Good morning, everyone. Welcome to session A1, Designing for Membrane Architecture. The PDH code for this session is 76846. Our speaker today is Marco Cano, professional engineer, holds a Bachelor of Science in Civil Engineering from Monterrey Tech in Mexico, a Master in Science in Civil Engineering from the University of Illinois at Urbana-Champaign, and a Master in Engineering and Membrane Structures from the Anhalt University of Applied Sciences in Germany. He is licensed in 7 states, in Mexico and Germany, and has over 12 years of experience. He is founder and CEO of Fractal Structural Engineering. In his time off, Marco enjoys woodworking, photography, and acoustic guitar. Please help me welcome Marco.
Thank you, Catherine. Good morning. So we're going to be talking about designing membrane structures. There's a lot of depth in a lot of what we're going to present here. So it's going to help a lot if you interrupt me a lot and ask me questions. If there's a slide that we're going to get to, I'll let you know. But if there's something that you're curious about, please interrupt me a lot. It works a lot better if you do. The first 2 slides we have to put in, so bear with me on those, and then we'll actually get started. Session description. This presentation will provide an overview of the analysis, design, and fabrication of membrane structures, with the hope of increasing collaboration between architects and engineers to design successful membrane structures. It will also discuss form finding to generate the geometry of our membrane structure, as well as designing assumptions, fabrication of our membrane structure, patterning, welding, and some typical connections. We're going to understand the step required for the design of a membrane structure. We're going to understand the definition of form-finding process. We're going to understand the difference between conventional structures and pneumatic membrane structures. And we're going to understand the review and the design approach for the 2 basic shapes of membrane structures. So this is kind of what we're going to be talking about. I'm going to show you a couple of examples. I'm going to try and refer back to some of them because they're very good examples of typical membrane structures. The one you see on the left is the Olympic Stadium in Munich, in Germany. And this is one of the structures that kind of started it all. You know, Fray Otto is kind of considered kind of the father of membrane structures. Architects will say he's an architect. Engineers, we claim it as one of our own. But it's very impressive because this was built for the 1972 Olympics. So the design of this was done in the 60s. So this is pre-computers. This is pre-finite element analysis, pre-Revit, pre-3D modeling, and all those things. So the fact that they were able to do these type of things it's pretty impressive. And the way they did it is they actually created a 8-foot actual model of the structure. And this is not just like an architectural aesthetics model. They actually created a structural model with actual steel mini members, mini cables, and everything. And what he did is he would take a photo of the structure. He would hang weights all over the structure to simulate load, snow loads, wind loads. And then he would take another photo. And he would overlap those photos, measure how much it would displace, and he would analyze how the structure behaved. So this was done in an era of very, very, very smart people that kind of started this whole process along. Now, the photo on the right, it's one that some of you might be familiar with, is the Denver airport. And the reason I put that one in is because some of you might have seen it. And also because a lot of people, when they think of membranes, they think of, a softer material, kind of a tent that you pitch in your backyard. And it's once you tense it, once you pre-stress it, once you erect it, they're very, very strong. You know, the amount of snow that this membrane gets, you can imagine. So they're very, very strong. They're very, very resilient. These 2 are very good examples of the 2 basic shapes that we're going to be kind of talking about. The one on the left is called the Sky Song Center in Arizona. And it's when somebody gets very creative and goes a little crazy. But you see, it's a series of cones. It's a series of inverted and vertical cones that get connected to each other. And the one on the right, it's the entrance to a racetrack in Germany. And this is what we call a sail. It's a structure that curves in two directions, but it doesn't have a conical shape to it. And then these two are two structures that we designed in our firm. And the one on the left is the Cuauhtémoc Stadium in Mexico. And what you're going to see is a lot of membrane structures are also used for facades. Okay, you'll see some examples further on of pneumatics that we use in some facades. And this stadium was an existing structure, and they wanted to kind of upgrade it and dress it up a little bit. So we put this facade of ETFE that we built as a pattern of mosaics on the outside. And then the one on the right is the Pascual Guerrero Stadium. And what happens with membrane structures is because they're very light, they're used a lot of times to retrofit existing structures. So, for example, we've done historical sites where they have an interior courtyard and they want to cover it to preserve it. We've done shopping malls that were built, as exterior shopping malls, and then it got way too hot, and they wanted to keep the traffic, so they covered them and they conditioned them, so they get used for those kinds of things a lot. And this was one of those uses. The seating was existing, was a concrete seating, and when Colombia they got like I think it was the sub-21 World Cup for soccer, they had to upgrade a bunch of their stadiums, and one of the things that they had to do was to include a roof over some of the seating. So without having to do any reinforcement to the steel structure, we were able to add these series of Calatrava trusses that support this membrane structure. So based on those examples, kind of what are they? For a membrane structure to be called a membrane structure, it has to have three characteristics, and it's what makes them different from, let's say, a fabric-covered roof. Okay, and the first is that it has to have a Gaussian curvature, and that's my geek speak for it has to curve in two directions. So if you remember a cone, it curves in the radial direction and it curves in the circumferential direction. So we derive a lot of the stability of the structure from having that double curvature. And in the sail, you can see that the two high points, there's a curvature that gets formed between the two high points, and there's a curvature that gets formed between the two low points. We need that double curvature, otherwise we can't consider it a membrane structure. Now we have to do it out of elastic materials. Okay, when we fabricate, we create a certain pattern, but it doesn't get its final shape until we stretch it and tighten it in place. And you can only do this if you have elastic materials. Okay, they stretch quite a bit, and if you think of a soccer ball or a basketball, it's created out of two-dimensional strips, and it's only when you apply the internal pressure to that ball that you actually get this nice round element. And then the third is when we talk about membrane structures, we're talking about tensile loads only. If you're familiar with Felix Candela and his work, he created these wonderful concrete shells. Well, those are three-dimensional structures for sure, and they're great structures, but those rely on compression and some bending, and that's not what we're going to be talking about here. In membrane structures, any compression loads and any shear loads are considered failures in the structure. So this is kind of what we're going to be talking about today. It's kind of the design process of what we have to go through. The first thing, and I'll point to kind of where some of the industries get involved. The form-finding process, this is kind of where architects play a lot. They start to try and get the shapes of kind of what we're going to be designing. And then we hand it over to kind of an engineer, and we start looking at what kind of loading are we going to put on these things. They are very unique. If you looked at the photos that I showed you, there's no two that you'd say, yeah, that one looks like this other one. They're very unique. So the loading gets very tricky because not a lot of codes cover how we load these things. Okay, and then we have to analyze them. As you might imagine, all of this, because we're not Fryoto and we can't always create models like he did, they're very computer intensive, and we have to be very precise in what we model. And then, once we get all the forces that we're going to have in both the steel structure and the membrane, we design it, we size it, and then there's a portion that's called the patterning, and we'll go through all these slides, and I'll let you know exactly what each of these things are. But at each of these stages, we might have to go back, and it's kind of a cyclical process. So we're going to go into form finding first. So we're going to start on the left side. And the way to think of form finding, we talk about, form follows function. And in membrane structures, it's one where it applies. And if you think of a rubber band and you stretch it between 2 points, and you take one and you perpendicular to it, you pull on it. Okay, you get the form in the left middle. And if you take 2 additional ones and you pull on it, you start to get kind of a curvature. And I hope you can see that depending on how hard I pull on those three rubber bands down, I get a more dramatic curvature. I get a more so the amount of pre-stress that I induce into my structure, it influences the final shape of what we're going to do. Now, if we go to the center, this is kind of thinking about it three-dimensionally, and you stretch the same rubber band, and you take another one, and you go orthogonally to it, and you pull on two sides to it. Then you get the center bottom image, and that's as far as my PowerPoint drawing skills go. So I'm gonna need your imagination to understand that if we put more transversely to that center one, you start to get a curvature as well. And if you put enough in both directions, then you get the image on the far right. Okay, that's kind of how we do it. And depending on how much we pull on both sides, then you start to get a more dramatic curvature. So how do we start? Well, we use programs for this. And what you start with is you start with a boundary condition. You start with, if you have this courtyard that you want to cover, then you start with the boundaries of the courtyard. Basically, your supports. Where are my supports going to be? So what you see here on the image on the left is kind of where we assigned support. We say the top cone, that's how high I want it to be because of architectural reasons. And the bottom is where I'm going to anchor it and where we're going to support it. So what it does, it creates a 2D plane between those boundary conditions that you're stating. You can see that those are flat, those are 2D, each one of those panels. And then you tell the computer, find me a shape with those boundary conditions. And it generates the image that you see on the right. But it's a little non-intuitive of how the computer starts with that first shape. How does it know to go from that one, from the left to the right? And I don't know how many architects are here, but if you're thinking about a building and you're trying to determine its initial shape, one way to start is with the golden ratio, right? A lot of Greeks started with the golden ratio. Man, even the ones that designed the iPhone started with the golden ratio. You say, well, let's start there. It's a shape that's pleasing to the eye, that exists in nature. Let's start there. Well, in memory structures, we have something similar to that, and we call it a minimal surface. Okay, and what a minimal surface is if you establish 2 boundary conditions, and you try to generate a surface between those 2 boundary conditions, the surface that creates the minimum area, that's called the minimal surface. Okay, and a lot of design people, architects that want to work with membrane structures, they do soap film structures. You take a wire hanger, soak it in soap, and start playing with it, start deforming it. And the surface that you get, it's a minimal surface. And what happens is there's a engineering phenomena that happens in which stresses in all directions in a soap film are equal. So that's how you create a minimal surface with a computer model. You tell the computer, find me a shape that has equal stresses in all directions, and that's what it generates. Now, I will say that not every boundary that you can think of will generate a minimal surface, but the computer will try and get close to it. Okay, it's, for example, if you take the image on the left there, two equal circles, and you start pulling them apart at exactly 1.6 of the diameter, that soap film will burst because you won't be able to find a minimal surface. It will basically turn into two kind of mirrors, is what it'll do. So if you're curious about how to find shapes, that's one exercise. Some people, instead of soap film, they do like pantyhose, and they start playing with that. So this is kind of one of the programs that, like if you go online, it's called Formfinder. It's free to try, and then if you want to export stuff, you can buy it. But if you establish a boundary condition, like a top and four corners, and you tell the program, give me a minimal surface for that condition, you would get the image in the center. That's the minimal surface for those boundary conditions. Yes?
So what sort of considerations would you have to make when you're form finding? Would you have to consider maybe forward thinking of the material that you're going to use so that you're form finding appropriately, if that makes any sense?
Yeah, so the question is, do you have to consider the final material that you're going to end up using while you're using form finding? And the answer is yes, because the more dramatic the shape that you wanted to make, let's say you wanted to make like the picture on the left, what happens is that you're going to have to induce a lot of stress to get that shape. And so to start with, you're going to have to be thinking, I'm going to have to use a stronger material to be able to accomplish that, because I'm going to induce a lot of stresses in that material. So yes, it's yes.
No, it's okay. Finish what you're saying.
Okay. So and a lot of times we can do this form finding process. Is a fairly fast and simple thing to do because you're kind of just playing with geometries. And when we see it, that this is where experience comes in. You'll say, we're going to have to start with this material and try to go from there. Yes.
So I'm having trouble seeing how the tension is applied in this one. How is it held at the top, for example?
Okay, and I'll show you. I'll show you how we achieve the different shapes and how we get to tensioning it. I'll show you here in a little bit. Absolutely. So if you establish a boundary condition, those corners and that top, and you ask the computer to generate a minimal surface, it will generate the image in the center. Now, if you're an architect and you say, you know what, that's too aggressive, that's too dramatic, I don't want that in my structure, I need something that is more subtle, something more elegant, well, then what you do is you relax the stresses in the circumferential direction, and you get the image that you get on your right, okay, something with less of a curvature. But if you're an architect and you say, you know what, I need something that makes an impact, something that's more dramatic, something aggressive, well, then you increase those radial stresses, those circumferential stresses, and you get the image that you get on your left. So you play with those stresses to generate different shapes. And I'll show you when we establish patterning how we do it so that you can get either the center, the right, or the left, or the left shapes. So once we establish a shape that you like, okay, we go through iterations, and you say that's what I want it to look in the end. Then we have to start loading it, okay, and like I said, a lot of the codes are not geared towards membrane structures. Okay, a lot of times we use wind tunnel testing if the project is large enough, but sometimes you have smaller projects that don't warrant or don't merit a wind tunnel test. So we have to try and extrapolate from the codes that we do have and try to get close to how the membrane structure is going to how it's going to react. Some of the membrane programs are starting to do like a virtual wind tunnel test. It's not entirely there yet. It's very complex when you get the geometries that we get. Wind loading is by far the biggest failure mode that we're going to have. These are basically big sails that are up in the air, and that's kind of what is going to affect a membrane structure the most. But you get some places like Denver that you get a lot of snow, and you get some places where it rains a lot. Rain is usually not a problem except when you're installing it. You have to get a good amount of time without rain, and I'll show you why. Because imagine you don't put it in place, you don't stress it in place, and water starts to accumulate. Well, the more it accumulates, the more it deforms, and you start to get more water and more water and more water, and all of a sudden it just you can't pump it out fast enough. Usually, this is kind of what happens. If they don't get it in place fast enough, you start to get these type of photos. This is another one where it happened. They couldn't tighten it in place, and they brought pumps in, and they couldn't get it fast enough. And legend has it, this is hearsay, okay, that the structure started groaning, and one of the police officers who was there started getting nervous, and he shot twice into the fabric to get holes in and drain the water. I've been told. So we have a shape that we like. We have an idea of the loading that we're going to put, and then we're going to get into the analysis. Now, there's a lot of assumptions that you have to make in membrane structures. And part of it is because membranes are not codified like we have with steel. Steel is a material that's been studied. We understand a lot of it. There's a very nice big code that we can follow. It tells us exactly what assumptions we can and we cannot make. But with membranes, it's a little bit different. And one of the biggest problems that's happening in the industry right now is, does the membrane brace the steel structure? You know, we understand that if we put a steel deck or if we put a composite deck, we can fairly assume that deck, if we weld it correctly, it's going to brace our structure. But if you have a membrane, the question is, does it? And how much? And what type of bracing does it provide? And there's not a lot of research done in that area. And the reason it's because the shapes are so varied that it's hard to codify. I mean, if you looked at the photos that I've shown you, well, you know, it's hard to say exactly what to research. The shapes vary a lot. So, and part of the problem is that right now, all of the membrane materials that are out there are driven by specific manufacturers. In other words, you have to get a catalog, get their properties, input them into your analysis program, and use them to design. With steel, it's a little different, right? We have a 36 steel, and regardless of who makes it or where they make it in the world, you can be fairly confident that you're going to get the steel that you specify. With membranes, it's a little different because it's driven by a manufacturer. So if that manufacturer tomorrow decides to discontinue that material, well, any research that was done with that material, it's kind of out the window. So the analysis and the analysis assumptions that we have to make, we have to be very careful about how we do it. In the European Union, they started getting a lot of membrane structures, and they said, well, you know, we can't codify it because we don't have enough research, but they established a guide on it's not part of the Eurocode yet, but a lot of people are pushing to include that guide as part of the code, just to have a guideline, just something to design by. So this is a project that we're working on right now. This was an existing baseball stadium that's going to be turned into an amphitheater. So this is a series of cones. There's a cone in the middle. There's 6 cones around the center, and then you have kind of a series of sails all around the perimeter. And so this is kind of what it would look like when we analyze it. We start loading it, and we get all the stresses in the membrane. And if we did our form finding right, we applied our loading right, and we picked the right material, hopefully that stress is less than what the materials, what the manufacturer specifies that we can take. Now, if it doesn't, this is where it gets a little bit tricky, because then we have to put a stronger material. But a stronger material deflects less, so it changes the shape again. So we kind of have to start the process over again. Now, when we were talking about assumptions and bracing assumptions, do we have any people from Dallas? Come on, don't be ashamed. Cowboys fans, come on. All right. Well, the Dallas Cowboys, they had a practice facility. And this was not a membrane structure. This was a fabric-covered roof. But the assumptions of bracing still apply. And what happened is that the company that was making these structures, they would erect the very light portal frame, and they would put these series of like trusses, and they were assuming that the fabric was bracing all of the compression cords. And well, you can see the results. If you have a chance to take a look at that, the report from National Institute of Standards and Testing, they basically, one of the conclusions was, we don't know if the membrane can brace the steel structure. And when you ran the analysis, assuming that the membrane braced the structure, you would get it to pass. Everything looked beautiful. And then you remove that bracing, and all of a sudden, they were overstressed by 500%. This one killed 2 people, so it's dangerous. The company that was doing these, they got this one to fail. They had a failure of another 3 or 4 of them before they basically posted a letter in their website saying, our structures are designed incorrectly. We don't have the manpower or the resources to fix them all, but we know that they have a problem. We suggest you fix them. And so right now we have to design a fairly conservative in lieu of having the research in place yet.
Do they go out of business?
Yes, absolutely. Yeah, basically, yeah. The only thing you would find on the website is that letter. Yeah. So that's the analysis. So if we started with a shape that we liked, and we applied the loading, we analyzed it, now we have a structure. Now we have to fabricate it, and we get into patterning. And this is where we start thinking about, well, how do we get to that final shape that we liked so much? So the patterning is the process by which we take a 3D curved structure and try to generate it with a 2-dimensional roll of material. Okay, so if you look, you get this is a very simple sail, and when you deconstruct it, you see that gaps form between the strips. You see those gaps. What happens is we will fabricate it as you see it there on the floor, and then we weld it, we fuse it, we stick it together. And it's a wrinkled mess when we do that, okay? Because you have a planar 2D fabric, and you're trying to weld a curve. So it's kind of a wrinkled mess. But once you stretch it in place, that's when that wrinkle smooths out. And if you designed it correctly, all the wrinkles will smooth out, and you get your curvature. Now, I hope you can see here that if that gap in the center or the gaps in the sides, that if we cut more of that material away, that's how you get more curvature. But it also takes more force to get it in place. So you induce additional internal forces like you were asking, how do we do it? And I'll show you here the example of a cone. So the more material you cut out, the higher forces you're going to have to pull with to get it in place and to get the final shape that you wanted. Okay, and there's a lot of this has a lot of very advanced engineering because everything is three-dimensional. There's no way to discretize this in 2D and simplify it. All of this is in 3 dimensions. So all of this has, for you engineers, if you want to get into it, there's a lot of very advanced mathematics. If you want to look at that paper of how they decompose a 3D shape into a pattern, it's a good read. So in the case of a cone, if you imagine this cone seen in plan view, well, what happens is you establish that you have a 3-foot roll of material. Okay, that's how the material is produced. So what you really have to do is you have to generate these patterns such that you can fabricate them in that roll. So when you have a computer program, you basically say, make strips that are no wider than 3 feet. And this is kind of what it would create. Okay. Now, one of the things that happens at this stage is that when we do form finding, when we do our analysis, when we go through all of those stages, we're assuming that the material is isotropic. Means we assume that the material behaves the same in every direction, regardless of which way I pull on it. But memory structures, a lot of the materials like PTFE, they do not behave that way. They are, if you imagine, the best I can say it is imagine a cloth that is weaved, and then you get two layers of plastic that get bonded to it. So it behaves orthotropically, so it behaves the same if I pull in the orthogonal directions of the weave, but if I pull diagonally on that weave, it behaves differently. So you can imagine that if I assume an isotropic material and then I establish a cutting pattern that pulls it in a different direction, it doesn't behave the way I want it to, and you get a lot of wrinkles. You might even get failure. So what happens is, once we establish a pattern, we have to actually run another analysis and decompose the stresses and make sure that once we get them in the orthogonal directions, that we still have a strong enough fabric. So there's an iteration process in there as well, depending. And sometimes, if you're very unfortunate, your patterning will tell you, use a stronger material. And a stronger material deflects less, and you have to start your form finding process again. It's not fun when you get to the patterning stage, and you don't have enough material. So I put this slide of detailing here right after patterning because, yes?
Sorry, can you thicken it to make up for that difference?
Yeah, so you can thicken it. What happens is, if you thicken it, when I keep the exact same strips, what it happens is your curve is less dramatic because it's a stronger material that deflects less. So you have to kind of start the form finding process again. It's sometimes, I don't know if you've ever had the pleasure of designing a cable, but what happens is you design a cable and you have to design for a certain deflection. But what happens is, if you end up with a cable that, well, it's not strong enough, and you put a stronger cable, well, that cable deflects now less, but it has a stronger force in it. So it's a very bad cyclical process. Yeah.
Keep using the word strength to describe the material.
Yes.
But it seems like there's 2 things you're looking at. One's the elasticity of it, and then how much you can stretch it before you actually get failure. Like, I can imagine a material that is very flexible that you could do all kinds of crazy things with because it just stretches forever. Okay. Or something that has no elasticity and breaks immediately or something.
Okay. So what he's asking me is that I'm using elasticity, or how much I can stretch a material, and strength. And here, if you get a sample of the material, okay, and you feel it, it will not feel like a balloon, okay? You won't feel that you can stretch it. That's when I talk about elastic materials, I'm talking under very high stresses, under a lot of load, we have to pull them with jacks. That's when you get your stretch. Yes, there's materials that will stretch more, and if you're familiar in steel with the elastic modulus, it tells us how much we can stretch steel, right? And here, what happens is you get two parameters from the manufacturers. You get a modulus of elasticity of the material and one that they call the apparent modulus of elasticity. Because what happens is if it's weaved, because this material is weaved, okay, there's a little slack in it when they fabricate it. So when you start to stretch it, it deforms without much load on it. So there's a deformation that happens there that is not due to the strength of the material, it's just basically taking out the slack. And then you get to a point where the material is taut, and then you start counting into so you have to load both parameters into your analysis. And what happens is it'll say, okay, I've reached my apparent modulus of elasticity. Now I'm deforming for the actual modulus of elasticity. So when we were talking about this patterning, and we're trying to fit it into a roll and the fabrication, what you have to think of is, how am I going to fabricate it? Because most of the time when you get two pieces of material, they get overlapped and fused together. And there's different, you can heat weld it, you have infrared, you have a lot of processes to create that connection. But you can imagine the one on the bottom is by far the one that's the most used. We typically don't use these two, although you could if you wanted to. But typically this is how we would get two pieces of material and overlap them. Well, but you can imagine that if you have a pattern that you liked, well, that's kind of butting them together, right? Well, you have to say how much force is going to go through that seam, there we go, through here, because do I have to overlap it an inch, 2 inches, 3, 4? How much? Depending on how much force is going through that connection is how much we're going to overlap. But if you're going to overlap, well, in your patterning, when you're creating your patterns, you're going to have this offset of the strip so that you can overlap it. And if you were very tight on your rolls, all of a sudden this overlap, you don't have enough material to achieve it. Okay? And then, so this is like some of the interior seams, and I'll show you what those seams look like once it's erected. But sometimes when we try and stretch it in place, we use a cable, and basically you create like a pocket, thread a cable through, and then pull on that cable to get it in place and to stretch it and generate the stresses that we need to create the shape. But if the strength that we need is a lot, or if we're worried that this pocket is going to tear, then we use a detail kind of like what they did here, where we get a material, we clamp two pieces of steel, and we pull on that steel so that we don't tear it. Okay, and that's kind of a photo of what this one would look like. So that's yes.
For the welded seam, are you applying like an epoxy or something?
No, typically you could, and that's how they did it originally. But the amount of force that we need to transfer through there, the epoxies that were being used, what started happening is they started dissolving the actual base material because these are membranes, and so most of the time what happens is it's done through infrared. You kind of weld those two things together. You kind of fuse them.
But you fuse them along that whole overlap?
Yes, right here it gets fused through all through that seam. Yes, yeah, and typically you can say, about 4 to 6 inch overlap is very typical of what you would see in most materials. Now, if you had like a courtyard, like an interior courtyard that you had boundaries that you had to adhere to, so you couldn't have this catenary of this cable in the boundary, And basically, you start looking at these sorts of details where you have to pull the fabric and the membrane to a rigid, straight, linear member. And there's, we have these that get threaded if the stresses are very, very small, or these type where we would pull from the back end and then clamp it in place and then release it. So you were asking how do we stretch it in place? So this is kind of a cone, okay? And cones, what they have is an interior mast, and sometimes that mast goes down to the floor, and sometimes it's a flying mast, the way it's shown here. I don't know if you architects, because the ones that I work with most of the times don't like columns a whole heck of a lot. They get into their spaces. So what happens is you can do a flying mast where you have an interior mast in the center of the cone, and then these cables off the floor go to the exterior, and then they get supported on the outside. So what you see here, you see all those lines. That's that welded seam. That's that overlap that we were talking about, where we get the material fabricated. That's how it looks aesthetically. So a portion of the design on the architectural side is also part of the patterning, because once the light shines on it, then you start to get, these kinds of aesthetics. Yes.
So that was a curiosity I had. So in the patterning phase, is a lot of that delegated to the engineer or the architect? So I'm sort of visualizing the conceptual form that, from an architect's perspective, this is what it needs to be. Mm-hmm. But maybe the nuances of understanding the patterning process would be more so for an engineer to consult on. So how does that process?
Okay, the question is how, if if an architect wants a specific pattern, and but the engineer has to apply to a specific strip and a specific behavior, how do we make that work? And the answer is with a lot of work. It's a very collaborative process. We in our firm we do a lot of conventional projects. Okay, a lot of buildings, a lot of those structures, and there's a certain amount of coordination. But because every decision that the engineer makes here has an aesthetic impact. If I change the material and I change your shape, you're going to be upset. If I get a cutting pattern that you don't like, and all of a sudden, instead of all these nice lines converging into a point, if I cut it in a different way, because I could cut this in a different way, instead of cutting radially, I can just slice across it. I've seen that structure as well. But if the architect wanted this look, well, so there's a lot of back and forth. And what happens in membrane structures is there's a few architects that specialize in membrane architecture, and they'll know. But a lot of times what happens is this is a specialty structure. If you think of your Avadex system, where you just say, I want this shape, and they show up and they design it, analyze it, fabricate it, install it for you. A lot of the people who are involved in membrane structures, that's kind of how they work. Okay, they'll kind of do the entire thing for you. Okay. So all of the things, everything that we've talked about so far, that's conventional membrane structures. Okay, those are the ones that you're going to see the most everywhere. Okay, but we have some pneumatic membrane structures, and fortunately, there's very famous examples of these. During the Beijing Olympics, anybody see that structure? Everybody? Okay, so that's the water cube. So in the water cube, they used it as a facade. Okay, and what they did is they used ETFE. Okay, and what each one of those cushions or bubbles is basically an inflated structure. There's curvature on both sides of this thing, and it's on the outside. It's held in place by a steel frame, and what happens is you induce an interior pressure to generate those shapes. But the process is exactly the same. We have to, depending on how much you want the bubble to pop out or in, and depending on your boundary conditions, you cut the material in different ways. But here, instead of the pre-stress being applied by cables that we pull on or a mast that we push up with cables, here the shape is achieved by inflating it more or inflating it less. So you have air circulating through those constantly. There's usually a pressure sensor inside of each one of those bubbles, and if it starts to lose pressure, a compressor somewhere in the building is going to shoot a little bit of air into it. And we do that because we derive stability from these things being taut or tensed. And with changes in temperature, changes in volume, we have to be able to keep on increasing the pressure. If in winter you lose a little bit of pressure, you need to increase it. And also because with also the changes in temperature, you might get humidity inside of these bubbles. So we're circulating the air and removing all of the humidity from the air. Now, the process of form finding, it looks remarkably similar. There's a lot of processes that overlap. But sometimes it's a little bit harder it's easier to think of a cable stretching fabric or a mast pushing up than it is sometimes to think of this bubble being inflated. Another fairly famous one, the Allianz Arena. This is Bayern Munich, where Bayern Munich plays. And what they do, so those are the same kind of cushions that we saw in the example. And here they also use it as a facade. And because this material, ETFE, you can get in clear color, they use it a lot because as you saw in the water cube, they illuminated blue here, but they can actually illuminate it in whatever color they want. And they've illuminated this in a mosaic pattern. Here I think it was like a national holiday, so they illuminated it as the German flag, but you could illuminate it in whatever pattern you want. Now, that's me in the orange jacket. We got to go to the location where they fabricated. Sometimes the scale of these things, each one of those, is one of those. So I put it there to scale. So these things are fairly massive, and you can see the steel structure that has to happen to be for this to be held in place. But in a more mundane setting, this is a shopping mall that we did, and this is one of these exterior shopping malls that got too hot, and they wanted to convert it to a conditioned space. So in between, we actually put an ETFE roof. So this ETFE is a clear material, and these, you can't actually see that those are bubbles, and that's good because we want it to be as clear as glass. But we took a photo from the outside just so that you could see it, and you can see the curvature of those bubbles. So that's taken from outside. So you get this cushion of air that spans between these two structures, and it's much lighter than glass, and that's kind of one of the appeals for retrofitting existing structures. So I'm glad that some of you asked questions. Also, in the interest of providing scale, I showed you a picture of the Pascual Guerrero Stadium that we did in Colombia. I've seen that photo a bunch of times, and it always impresses me because the scale of that is also kind of misleading. See, that's a person right there. So the amount of structure or the amount of roof covering that we were able to provide without reinforcing the existing structure, it's one of the main uses that we do for membrane structures. And that's it. Do you have any more questions? Yes?
How do they do the lift of the fabric? Do they stitch it all and lift the whole thing up?
Most of the time, what happens is it gets fabricated in a shop, especially ETFE. ETFE, the welding process for ETFE, because it's clear, it has to be done in a dust-free, sterile environment. So all of that gets done in a shop. And then it gets folded, and it's shipped in rolls, in crates. It gets unfolded in the field, and then a lot of times, think of this as kind of your steel structures or your tilt wall panels that you design them for the in-place condition. But we also have to say, okay, if we're going to lift it from this end, make sure that it doesn't rip when I lift it from a single point because it's so heavy. But you lift it with a crane and you start to anchor it in place.
Do they reinforce the attachment points? I mean, because you said when the crane lifts it, you could rip it from a corner because the stresses are supposed to be even.
Correct.
Along the edges.
Correct. And so yes, the question is, do they reinforce it? Do they reinforce the fabric in the point of lift? So yes, if we find we establish a lifting procedure, and we say, okay, we're going to lift it from this point. Okay, run the analysis. Can we lift it from that point? And if the answer is yes, then you need to reinforce it. If the answer is yes, we need to reinforce it, then then what we usually do is we weld an exterior patch to that membrane that is very strong. Okay, something that we can cut away once we have it in place. Because what we don't want to do is put a patch of material and reinforce on a membrane that is very dependent on, if we establish a form finding process and a cutting pattern, if you all of a sudden come back and reinforce a portion of it, you get a part of the structure that behaves differently from what you thought it was going to. So we try to, any reinforcement and lifting that we need to do, we do it exterior to the material that we have. Yes?
The factors of safety and elongation, what kind of factors of safety are the manufacturers requesting on their materials, and what kind of elongations do you get?
With elongations, I'm not sure. The elongations in these things, they're not codified as far as kind of deflections go. It's more of a, because these, when we analyze these, okay, we're talking we're theory of large deformations. Okay, when we analyze a steel structure, right, we kind of assume that the original geometry is very close to the deformed geometry. That's not the case in membrane structures. They deform a lot. Okay, deflections of 6, 8, 12 inches is very.
I understand the difference between small and large deflections. What I'm asking is, if I took a piece and did a uniaxial or biaxial tension test on it, I stretched it two directions, what kind of elongations do I get before this ruptures? Any idea? I mean, it differs by manufacturer, obviously.
Yeah, it's. Yeah, and I'm not sure. And it.
On the spot, I don't need
No, it's okay. No, what happens is it's a hard question to answer because if, for example, Sergi Ferrari is one of the manufacturers, one of the largest in the world, and they have over 200 materials. So they have something that'll last 2 years, that is kind of a temporary kind of thing. And that material, it's closer to a balloon. You can stretch it by hand. Okay, and then you have the kind of the Denver Airport type of membrane where it's very, very strong and you can't move it if you tried. So the variation in elongation it's a lot between the manufacturers and between the materials. Yeah.
And off the top of your head, do you have any information on the factors of safety these manufacturers want to
typically what they do is they say factor of safety of 2. So they give you go to this stress, and you'll have a factor of safety of 2. It's what they will do, and then we do ours, precisely because these are not ASTM materials. They err on the side of caution, and if you saw those the photos, if we go back to the photo of the rain problems, you can see that even with that amount of water, the fabric is not failing, right? It's not designed for that amount. What happens is in a fabric, there's so much redundancy that it's extremely rare to see the membrane fail. Most of the time, the failure is the supporting structure in a fabric. Yes?
The Denver with the snow,
what happens in Denver with the snow? Okay, so part of the design of membrane structures is that when you establish a shape, a form that you like, you have to make sure that you don't have any what we call flat spots. You always want your rain and your snow to slush off. But with snow, it's not as easy as with rain. You get some accumulation. So we designed it for a certain amount of accumulation, and for the deformation that happens due to that accumulation to not create a divot in the structure, so that it can eventually slosh off. And it's kind of like you would design kind of any roof in Denver, right? You design it for a certain amount of snow load, with the assumption that there's a peak snow load, and after that it kind of falls away depending on your slopes. Now here it gets a little more tricky, right? Because snow loads are dependent on slope, and if you saw our structures, well, the slope it varies quite a bit. So we have to do a lot more work. Yes. The question is, what's the limitation of an individual piece? It depends on the manufacturer. Most of these materials are fabricated in Europe, and so they usually come in 1 meter widths. That's one strip. So your patterning, it will always be kind of within that strip. Now, for some projects, one of our partners is doing one of the Qatar stadiums, and they had a lot of fabric for one of those stadiums. So what they requested is that the manufacturer do a 2 meter run, so a 2 meter width, because they didn't want the amount of welding that they were having to do, the number of strips was a lot more than if they just said do a larger run with less seams on it. Generally, I say it's 3 feet. It's a 1 meter width usually. Yes.
On the cube, it seemed like after a couple of years, the quality deteriorated. Was that because of dirt in the air getting inside the cube?
Yes. Well, no, not inside the cube. Usually outside. Depending on how good a care they take of the facade and how it lasts more or less. ETFE will last for a long time, and there's different qualities of ETFE. Part of the problem is pollution there. It rains, and acid rain is fairly damaging depending on the caliber of ETFE that you use. And also, there's an element of luck in there. If a bird flies in beak first, it'll puncture it. And you have a decision to make. You can either patch it, in which case you'll have a kind of a darkened spot, let's say, or you can replace the panel. Okay, most of the time, if it's a fairly iconic structure, they'll replace the entire panel to do that. Yes.
Yeah. That makes me think of what is the service life on these materials, and also is there like a creep and relaxation that you have to worry about as well?
Yes, there's a creep that happens, and we consider some of it, but because they're very elastic, it's not as much as you would think. There's a very small factor of relaxation in this, especially because the relaxation comes a lot into play when you're losing that apparent modulus of elasticity. Now, as far as of shelf life. It depends on the material that you pick, and that's one of the questions that you have to answer very early on. Is, well, how long do I want it to be there? And there's materials there that are rated for 75, 80 years, no problem. They're much more expensive than if you get a 10-year or 5-year material. And she's going to hit you if we keep asking questions. But it's her fault.
All right, thank you.
Yeah.
Are you able to estimate loads for the main structure or support early on in the design, or does that come after planning?
Yes, I can estimate the weight of the support structure fairly early, unless the form finding process gets a little crazy. So I can estimate it, let's say, for the minimal structure, for the minimal surface. Okay. Now, if you decide that you want a more dramatic kind of a thing, then the stresses start to shoot up quite quickly. And at that point, my support structure is going to shoot up quite quickly. Yes?
Insulation value on the fabrics, because there's a huge amount of envelope. Is it just heat loss, or?
They actually, manufacturers establish R values on a lot of their fabrics, and you can, and I've been to expos where they have different kind of rooms with different kind of material, and the amount of heat transfer what they can vary with the heat transfer is significant. It's pretty advanced. Now, if you have a real problem of where you want to keep something fairly cool or fairly warm, then one of your options is to actually do the bubbles, because those bubbles, those have a tremendous amount of thermal insulation, especially because you can circulate air and you can decide what temperature that air circulates at. Thank you so much. Sorry? Huh? Oh, yes. Sorry. You guys do not get credit unless we ask a question. Give me just a second. Okay. So the assessment question. Name one step required in the design of a membrane structure. So this is going to be by a show of hands. Okay. So A, form finding analysis is an important step in the design of a membrane structure. B, determine the color of the final installation. C, determine the expected completion date as required by the end user. How many think A? Okay, you all paid attention. Write down your PDH code for those of you who need credit for your professional development hours.